Hello everyone, welcome to OneClass. My name is Shanjida and today I'll be going over some commonly asked chemistry questions both at the high school / university and college levels. And so I'm currently a second year human biology student studying at U of T. And lastly, if anyone needs additional schoolwork help or needs tutoring, you guys could check out the description box below. And other than that, let's get started. So our first question here says, what is the structure of a cyclohexane? And so, as it's stated here, is that a cyclohexane is a cyclical alkane, meaning it only has single bonds in structure, forming a ring, and its chemical formula. So let's write. So a cyclohexane, right? It has a chemical formula of C6H12. Okay. So since it's a cyclohexane, one way to draw structure of a cyclohexane is by sketching a hexagon. That is, we have here 1, 2, 3, 4, 5, 6 carbons, and you're not showing your hydrogens. So this is your a cyclohexane, and the compound can also be drawn by its chair conformation. So we can draw a cyclohexane in the chair conformation. So chair con. Okay, and so we're going to draw the chair conformation of its most stable form. And so you would have something like this. And you would have your hydrogens. So in this case, I will draw out the hydrogens. Use a different color. Okay, so I'll use all the axial ones in red. Right here, so you have 12 hydrogens, right? So one going down here. Okay, so these are all your axial hydrogens, and then now I'm gonna draw all the equatorial hydrogens going like so. Okay, so if you count up the hydrogens, so 2, 4, 6, 8, 10, 12, you have 12 hydrogens, and so this is your basically most stable conformation. So most stable conformation, chair conformation of your of this of a cyclohexane. Okay, and so this is our answer. Okay, so yeah, you can see that this is what we've got. The solution here is correct. Okay, so our second question says, distinguish between the terms electronegativity versus electron affinity, covalent bond versus ionic bond, and pure covalent bond versus a polar covalent bond, and characterize the types of bonds in terms of electronegativity difference. Energetically, why do ionic and covalent bonds form? Okay, so this is a very big question. And so what we can start off by saying is that electronegativity is a chemical property that says how well an atom can attract electrons towards itself. So let's say for electronegativity. So in simple terms, electronegativity means how strong um, an atom is. An atom is in terms of pulling the electron towards itself. Okay, so it's basically you're like holding on to the electron, and that's what basically electronegativity is, or how it can attract electrons towards itself. Where your electron affinity this is where it's stated that the electroaffinity of an atom or molecule is defined as the amount of energy released. So amount of energy released by an atom when an electron is added. So when is added. So as you can see, these two are electronegativity and electron affinity is two different things. So added to a neutral atom. Right? In this case, you are measuring or a neutral atom or a gas. Okay, so in this case, you can see how electronegativity differs from electron affinity. This is where you are basically calculating how strong the atom is, whereas electron affinity is more of the energy. We're talking about energy. And so this is basically the key difference between the two. And let's now talk about ionic and covalent bonds. And so the main difference in between an ionic and a covalent bond, main difference between a covalent and an ionic bond is the atoms in the bond. Okay, and what I mean by this is, so let's first address an ionic bond. So let's say for ionic, so for an ionic bond, we know that this is formed between a non-metal and a metal, right? And for example, we can say right? So your Na is your metal here, and Cl is your. And we know this by looking at the periodic table. We know that our group 1 and group 2 are, and group 3 are metals, and then going on from group 4, they're all non-metals. So we know that and always our metal goes first in the name. So we know, so this, right, forms NaCl. And the bond between Na and Cl is an ionic bond. So this right here, this is your ionic bond that is holding them together. Okay. And so, okay, that was for ionic. Now let's now move on to covalent. So let's say covalent. And we know that a covalent bond is formed between two non-metals, right? Anything from a group 4 and onwards. And so your covalent bonds are between non-metals. So for example, we can have let's say carbon carbon plus, right? So we know that carbon is a non-metal and oxygen is also a non-metal. And so this is a form of covalent bond. So we can say that bond between the two, so the bond right here, this is your covalent bond. And one other property or aspect of covalent bonds is that atoms form a covalent bond in order to reach a more stable state, right? So let's write this. Atoms form a covalent bond in order to reach a more stable state. More stable state. And we know in covalent bonds that our electrons, so in covalent bonds, the electrons are being shared. So they're not being gained or lost, right? We're not, and not being. So in other words, we're not losing or gaining electrons, whereas for our ionic bonds, electrons, the electrons in this case are being gained slash like losers. Or like losers, right? So 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 like for example, from our NaCl example, our so our sodium over here it has a positive charge. That means it loses its electron and it gives it to our are chlorine, right? So you're transferring electrons here. So we can say what we can say is that are being transferred. And so this is the main difference. These are the main difference between a covalent and a ionic bond. And lastly, we have to address pure covalent bond versus a polar covalent bond. So in pure covalent bonds, so pure covalent bonds, this is where your electrons are being shared equally. So you don't have a net charge. So no net charge. However, in polar covalent bonds, so in contrast to this, polar covalent bonds, the electrons are shared unequally. So you have still have partial charges. So you basically have partial charges between the atom, and overall you have a net charge. And also, as an atom exerts a stronger force of attraction on the electrons than the other, this is where you have electronegativity comes into place. So in this case, electronegativity. So basically the difference in electronegativity between two atoms this is what determines how polar a bond will be. And so basically, this is the key difference between polar covalent bonds and pure covalent bonds. Okay. And also the same thing for covalent and ionic, and also electron affinity and electronegativity. And so we can see that don't use an electron, right? You're transferring electrons between ionic, whereas you're just sharing in covalent bonds, right? And being shared between atoms. And pure covalent is where your electrons are being shared equally. In polar covalent, in pure covalent, your electrons are being shared. In polar covalent, the electrons are being shared unequally, and you have electronegativity in place, and then the difference between the electronegativity of the atoms determines how polar the bond will be. So the solution here is correct. Okay, so our next question says, what are the Lewis formulas of the following ions? Okay, so in writing Lewis structures, we need to basically count the total number of electrons that is over here. So what is stated here, the total number of electrons that need to be distributed is counted first by adding the valence electrons of each atom, and then you form the formal charge, and then a skeletal structure is first written by distributing bond electron pairs and then lone pairs, and then lastly your formal charges will be added. That and then formal charges are added to the atom if the number of electrons does not satisfy the octet rule, and therefore the structure with the least number of formal charges or have the smaller charge is the most stable Lewis structure. So let's start off with A. In this case, we have iodine bromide and dibromide. So the atoms of, let's write this. Okay, well, this is a positive, and so what we have to do is find the total number of electrons. So we have iodine. Iodine, where is iodine? Okay, so iodine is right here, right? So iodine is in group 7, so we know that it has 7 valence electrons. So iodine, 7 valence electrons. Now we have to look at bromine, which also has 7. In this case, we have 2, so we will multiply that by 2. And so you have 14 valence electrons for 2 bromines. You add them up to get your total, and you should get 21 valence electrons in total. Okay. And so 4 electrons are being distributed in 2 bonding pairs. So since we know we have 2 bromines and 1 iodine, we know that we would form 2 bonds. And so 4 electrons will be distributed into those 2 bonding pairs, while 16 are distributed as lone pairs in the atom. And then so you have basically 16 plus 4, you have 20 of them bonding, and you're missing 1 electron, which is and basically that will contribute as the formal charge. So let's begin drawing. And we have and so we know that 4 electrons are being shared in these 2 bonds, and then that leaves us with 16 bonding or lone pair as lone pair. So let's get. We know that bromine has 7 electrons, right? And 1 of them are being shared, so we know it has 6. Yep, 6 electrons. So we would have 3 lone pairs. That goes for the same as this bromine. So we know that we have 2, 4, 6, 12, 12 electrons, right? And so now we need 2 more lone pairs, and that would go on iodine. So in this case, we have a total of 20 valence electrons being shared or being occupied right now, and so we're missing 1. And since that 1 is not being occupied, we say that this structure has a formal charge of since we didn't add that 1 electron, right? Since electrons carry negative charge, we didn't add a negative charge, so you basically you don't have a negative charge, and because of that, our compound here is positive. And now let's go to our next one, which is C. We do the same steps for B, which is chlorine dichloride, ClF, right? Okay, so now what we need to do, let's first find the total number of valence electrons. And so you have chlorine, and we know that chlorine is in group 7, right? And it has 7 valence electrons. We have 2 fluorine atoms, so we have 2. And we know fluorine is also in group 7, so 7 times 2 is 14, so 14 valence electrons. And so now you just add them up. So the total number of valence electrons we have is 21 valence electrons. Okay, and so now since we know that we have 2 fluorine atoms and 1 chlorine, we know that we will have two bonds, and in those 2 bonds we would have 4 electrons being shared, right? And so we can basically draw this out now. We have chlorine, right? So out of the 21, 4 of them are bonding, and now the rest would be our lone pairs. And so let's start off with addressing fluorine, and since fluorine has 7 valence electrons and 1 of them are sharing, we have 6 valence electrons, and those 6 would be added as 3 lone pairs. The same thing goes for this fluorine. And so we are done. So we just addressed 12 electrons, right? 12 plus 4, 16. And chlorine in this case would have 2 lone pairs, right? And so, and then the formal charge. So if you guys count the total number of electrons, we have 2, 4, 6, 8, 10, 12, 14, 16, and 18, or 20, sorry. So we have 20 being shared, right? And so what we can say is that this structure also has a formal charge of +1, since we're missing 1 valence electron that is not being occupied. Okay? So this is how the structure looks like. And lastly, we have cyanide. So okay, so let's find the full number of valence electrons. So carbon has 4 valence electrons. And nitrogen has 5. And so total number of valence electrons is and so 6 electrons. So in this case, cyanide forms a triple bond, and in the triple bond, we would have 6 electrons being shared, while 4 are in 2 lone pairs. So let's draw this out. So you have a triple bond, and then you have this. So we know that 6 of them are being shared, right? 2, 4, 6, and that leaves us with 3 more electrons. And so in this case, you can see that nitrogen only can form 3 bonds, and so it did. So it doesn't have any more. It can't form any other bonds. So in this case, what we say is that carbon has has a lone pair of electrons. And so in this case, we have, in this case, as you can see, also nitrogen would also have two lone pairs, right? Since it has 5 valence electrons, it can only form 3 bonds, and 2 of them are left out. So this makes this. So in this case, we added one more electron. So this whole compound here, molecule here, would have a charge of negative. Okay. So, and the negative will go on the most electronegative atom, and in this case, so this is our electronegativity chart. You can see that nitrogen is more electronegative than carbon, so the negative would be, and so this is your solution, and so yeah, okay, this is what odds, and the last one would also have a negative. Actually, I think to make it more stable, it would be on least negative electronegative. So okay, so our next question says, how do you find the molar mass of argon? Okay, so molar mass, I'm denoting as capital M as molar mass. Argon is written symbolically as AR, uppercase A, lowercase r. And to find the molar mass, since argon is an element, this is actually given in your periodic table. So if you look at argon here, it's a noble gas. So it has a molar mass of 39.95. However, you can find the molar mass or the atomic mass, which are the same thing. So we can say this is equal to your atomic mass. And we know that atomic mass is found by calculating the number of protons plus the number of neutrons. And in this case, your number of protons is your atomic number, which is 18. And so in most cases, the number of neutrons is the same as your number of protons. So we could say this is, and so this would give us 36, right? And you can see it's somewhat close, but we won't really do this because this is only for AN atomic mass. And so since looking at our periodic table, we can see that this is 39.95, and the units for molar mass is per. Yeah, so this is your 39.948. This is your molar mass. So this. Okay, so our next question says, rank the following compounds according to their boiling point, lowest to highest. So we're given 4 compounds here, and we would want to find the boiling point. And so, as it's stated here, is that one way to classify or to arrange the boiling point of the given compounds is to basically know what forces are present, especially intermolecular forces. And so if you have a strong force, that means they will have a higher boiling point because you would have a harder time separating the molecules, right? So we can say strong. I'm just going to write intermolecular forces as IMF. So is equal to high boiling. just gonna write BP as boiling point. Okay. And so higher energy is needed in terms of heating, means you need higher temperature in that case, right? High BP, and then you need more energy. And so this is basically needed. So when we're talking about boiling point, we're basically stating physical change from, let's say, solid to liquid, liquid to a gas, right? And so let's start off with calcium carbonate. So example 1, calcium carbonate. And so this is an example of an ionic compound. So this is an ionic compound because we know calcium is a metal. Okay. And so ionic compounds are one of the strongest, is the strongest intermolecular force. So I'll write this. So this is the strongest intermolecular force that is present in the bond. And so this is the strongest of them all. So this is the strongest, or like this will have the highest point. Boiling point. So we can say this is number 1 for being most being the most strongest. Okay, and so all of the rest, as you can see, methane, methanol, dimethyl ether, have covalent bonding. And so let's start off. Let's start with let's then do methane. Okay, so methane. Let's see. So CH4, so it's basically CH4 has this has this has this has dipole forces. Dipole. And London dispersion. And so this is nonpolar because this is nonpolar, as you know that the electronegativity of carbon and hydrogen is basically the same, so they cancel out. And so this having nonpolar dipole and London dispersion, you can probably say that this is very weak, and so we can say that this is the weakest. So weakest, this is the weakest bond strength. So this would be the would have the lowest boiling point. I would rank this number for being the least. Okay. And so let's look at the other one. Let's look at methanol. So CH4. And so methanol can be written as this could be written as CH3OH. Okay, and so this form shows there's hydrogen bonding. Okay, so we know that hydrogen bonding is strong and strong force. And which means that this compound possesses a very strong, so this would basically be one of the strongest. So in this case, it would have a high boiling point. But we don't know yet for sure if it would have the highest, since we have to judge the last one, which is dimethyl ether. So let's do that. Dimethyl ether. So we have CH3 OC, right? And so dimethyl ether is a polar. So this is polar. And you can see there's also hydrogen bonding. And since it's polar in nature, it has dipole-dipole. Intermolecular forces. And so, which means that, oh, sorry, this does not have. Okay, so it's pretty polar. And so because of this, there's dipole-dipole. And since it's dipole-dipole, since we know that dipole-dipole is weaker than hydrogen, you can say this is weak. So this would have a low boiling point. So the only thing we need to now compare are these two, and we can say that methanol is our second, and this is our third. So now to rank from it said lowest to highest. We know that CH4 is the lowest. CH4, and then we have a CH3 or CH3. And then we have CH4O, right? And then lastly, we have calcium. So this is your lowest, so increasing. So let's see this. So they wrote CH4 two times, but it was supposed to be CH4. CH4O two times, so it's going to be CH4, CH3, O, CH3, H4, O, and CHCO. Okay. Okay, our next question says, what is the molar mass of magnesium? So we know that magnesium is an element, so the molar mass is given in your periodic table, which is in group 2, right? Magnesium is in group 2, so the molar mass of this is 24.31 grams per mole. So the units for molar mass is grams per mole. So this is your answer. Okay, so next question says, what is the molecular weight of oxygen? And so oxygen exists as a diatomic molecule, so like gas, right? Diatomic. So this is your diatomic. gas. And so from the periodic table over here, we can say this is the molar mass of one oxygen. So the molar mass of O2 is equal to 16, so 2 times 16 grams per mole. And so this is 32.00 grams. So the molar mass of O2, or diatomic oxygen here, is 32.00 grams per mole. Okay. Multi-solution. Okay, so our next question says, what is the molecular geometry of CH3CHCl2? And so as it's stated here, in order to predict the geometry of a small compound, we focus on the central atom. So in this case, it would be carbon, and count the number of sigma bonds and lone pairs. And so the number of sigma bonds and lone pairs is called the steric number. And this indicates that the number of electron pairs present, bonding and non-bonding, that are repelling each other. And so the repulsion causes the electron pairs to arrange themselves in three-dimensional space, to achieve maximum distance from each other. And as a result, the geometry is basically dependent upon the steric number. And so if the steric number is 4, so let's say if the steric number is 4, then the atom will be sp3. So this is where you don't have double bonds, right? Atom will be sp3 hybridized. And the electronic arrangement will be tetrahedron. Electron arrangement will be tetrahedron. And so if the steric number is 3, then the atom will be sp2. So steric, let's draw a trend here. So steric is equal to 3. Then you have sp2 hybridized. And so then the arrangement will be trigonal planar. And so if the steric number is equal to 2, then you have sp hybridized. And so this would be trigonal. And this would be linear. And in this case, CHCl3 has 4 sigma bonds and 0 lone pairs. Okay, so you can write CHCl3 has 4 sigma bonds and 0 lone pairs. And so the geometry of this would be and so since the steric number is 4, right, the number of sigma bonds, you would have a tetrahedral shape. So actually it would be You have carbon as your central atom, chlorine, hydrogen, and then you would have chlorine over here. Since it has no double bonds, right? And the steric number is 4. So you just write the lone pairs, the chlorine. And what we mean by no lone pairs on the carbon, right? And so this is basically the geometry of this compound here. Okay. So you can see this is so the solution here is okay. So our next question says, what is the molar mass of sodium hydroxide? Molar mass of sodium. So this is the chemical formula for sodium hydroxide. This is very crucial to know to find molar mass since we're given a compound, right? And to find molar mass, it is important to know like how many atoms are there in the compound. That will tell you the exact number for your molar mass. So let's break this compound down into their individual atoms. In this case, we have the molar mass of sodium plus the molar mass of oxygen plus the molar mass of hydrogen. Right? So we know that the molar mass of sodium, if we look at the periodic table here, is 22.99. So we have 22.9 grams per mole plus the molar mass of oxygen, which is 16.00 grams per mole, plus hydrogen, the molar mass of hydrogen, which is 1.0 grams per mole. So the last step would be to add these three numbers together, and you would get 40.0 grams per mole. And so the molar mass of sodium hydroxide is 40.0 grams per mole. So yeah, the solution. Okay, so the next question says, how do you write the formula for calcium fluoride? So formula calcium fluoride. Okay. And so basically, as they state here, the formation of the compound is due to ionic bonding, since we know. So let's take this. So calcium fluoride is ionic bond, since we know that calcium is our metal. Fluorine, right, is our non-metal. And so the rule on identifying the chemical formula of a compound are to first, so like as they said here, name is started with the chemical symbol. So you need to know the chemical symbol of the compound. of the individual atoms in the compound. So chemical symbol, right? In this case, the chemical symbol of the cation followed by the chemical symbol of the anion. Since we're dealing with ionic bonds, we have a cation and an anion, and in an ionic bond, the metals are always our cation. So this is your anion. So the chemical symbols for calcium is Ca, and for fluorine is F. And so the next step would be to find the subscript for the second molecule is the oxidation state of the cation. So basically what we're saying here to find the subscript of the subscript for the first molecule, which is our cation, which is calcium. And so the charge for that, as we know that it exists in our group 2, it has a charge of +2. Right? And fluorine is in group 7, and this has a charge of -1. And so a last step would be to basically the subscript for the second molecule, and then the subscript for the second molecule would be the oxidation state of the cation. So what we have to do is we basically crisscross the charges, and they become your subscripts. And so what we have, so the -1, so it's not the negative, it's just the 1 that becomes the subscript of calcium. And so we don't put a 1, and the 2 from the calcium is the subscript for fluorine. So you have CaF2. Okay, so the chemical formula for calcium fluoride is CaF. So the solution here is correct. Okay, so basically that was the end of our session. If you like this Q&A, please subscribe to the OneClass channel. Share, comment, like this video, and if anyone has their personal questions about related topics or needs one-on-one tutoring sessions, you guys could check out the description box and follow the links to ask your questions. And other than that, I am Shanjida, and I hope to see you guys soon.